So in this video we are going to discuss the question in thermal and statistical physics which appeared in CSIR JRF examination that occurred in December 2015. So let's continue with first question. The statement is the heat capacity of the interior of refrigerator is. So we are given the heat capacity CV, that is equal to CV is equal to 4.2 kilojoule per Kelvin. That's the CV. Okay, the minimum work that must be done to lower the internal temperature from 18 degrees Celsius to 17 degrees Celsius when the outside temperature is 27 degrees Celsius will be. So what we will do is we will draw the schematic diagram and then it will be easy to grasp the problem. So here the temperature, this is the high temperature reservoir and this is at 27 degrees Celsius. We call this as T1, which is equal to 27 degrees Celsius, and in Kelvin this is 300 Kelvin. Okay, and the temperature of the lower reservoir, it's changed from 18 degrees Celsius to 17 degrees Celsius. So there is a temperature difference of 1 degree Kelvin, and the corresponding temperature in Kelvin will be 291 Kelvin, and here it is 290 Kelvin. Okay, so this is the schematic diagram, this entire cyclic process. So here Q1 amount of heat, it will be taken by the working substance from the upper reservoir, and here Q2 will be rejected, and net work done that will be achieved, that is W, that is equal to Q1 minus Q2. Okay, so now we have to evaluate what is the minimum work done, that's W, that is required to execute this process. Okay, so here the efficiency, we know that this is connected with the temperature of the reservoir. Okay, so efficiency is given by 1 minus T2 upon T1. Okay, so here the point is that which temperature we are going to take for the T2, the low temperature reservoir, and it's going to the final temperature here. Okay, so 1 minus the final temperature, that is 290 Kelvin, divided by T1, which is 300. Okay, so if you evaluate this quantity, so this will come out to be equal to 0.033. Okay, let's call this as equation 1. Now we want to evaluate what is the amount Q1 that is taken by the working substance, and that is given by Q1 will be, that is the heat capacity of the interior of the refrigerator CV, and the amount by which the temperature is changed, so CV dt, and that is equal to, CV is given to us 4.2 kilojoule per Kelvin multiplied by dt. So temperature changes, it is by one unit, so 1 Kelvin you can say, because it's the dt is that difference in temperature. Okay, so whether you take it in Celsius or in Kelvin, it doesn't matter. Okay, so this is 4.2 kilojoule basically, so this is equal to 4.2 kilojoule. Okay, now W, by making use of another relationship that connects the efficiency is also equal to the output, which is the work done, divided by input, that is Q1. So this implies the W shall be equal to Q1 multiplied by eta, and Q1 is 4.2 kilojoule and the efficiency is 0.033, and when you multiply these two numbers, so the number that we obtained, that is equal to 0.14 kilojoule. So this is the minimum amount of work done that we need to do in order to change the temperature of the internal of the reservoir from 18 degrees Celsius to 17 degrees Celsius. Therefore D is the correct option here. So let's continue with next problem. The statement is, for a system of independent non-interacting one-dimensional oscillator, the value of the free energy per oscillator in the limit t approaching 0 is given by. So we are given a system of n oscillators. Okay, so first of all, what we are going to do is we will find the partition function for one single oscillator, and from there we will find the partition function for n independent and non-interacting 1D oscillators. Okay, and once the partition function is known to us, from there immediately we can determine the required expression for the free energy. Okay, so let's continue with the single oscillator. So for single oscillator, partition function Z1 is equal to sum over all states exponential minus beta En. We know that for the oscillator, the energy spectrum is given by n plus half h cut omega, where n can take value from 0, 1, 2 and so on. Okay, so here summation is over n. Okay, so when we assign the values for n starting from 0, 1, 2 and so on, so the partition function that we obtain is given by exponential. So when n is equal to 0, we will have energy equal to h cut omega by 2. So here we will have exponential minus beta h cut omega by 2 plus the second term when n is equal to 1, so 1 plus 1 by 2, that will give us 3 by 2 exponential minus beta, or you can say exponential minus 3 beta h cut omega divided by 2, and the next term will be exponential minus 5 by 2 beta h cut omega plus so on. Okay, so from here we can take exponential minus beta h cut omega by 2 outside, and then inside the bracket we will be left with 1 plus exponential minus beta h cut omega plus exponential minus 2 beta h cut omega plus so on. And here this is a infinite series. Okay, and this is equal to exponential minus beta h cut omega by 2 divided by its the sum to this series will be a upon 1 minus r, where common ratio is exponential minus beta h cut omega. Okay, so divided by 1 minus exponential minus beta h cut omega. So let's call this as our result 1. Okay, so from here we can immediately determine the partition function for n such oscillator, n such one-dimensional independent oscillator, and that is equal to Z1 power n. Okay, and okay, we can even solve this equation further. So this Z1 is equal to, we will take exponential minus beta h cut omega by 2 in the denominator, and this is equal to 1 upon exponential beta h cut omega by 2 minus exponential minus beta h cut omega by 2. So we will call this as equation 1. Okay, so Z1 power n will be 1 upon e power beta h cut omega by 2 minus exponential minus beta h cut omega by 2 and its power n. Okay, now from here one can quickly determine the Helmholtz free energy. Let's call this as equation 2. So Helmholtz free energy A, it is connected with the partition function as A is equal to KT ln Zn. Okay, so when we will assign Zn here for n oscillator. Okay, so n will come before the logarithmic factor, so it will be minus nkt, and when we will bring these terms into in the numerator side, so then additional negative sign will come while taking the logarithmic. So that negative sign will be settled with this negative sign. So ultimately we will be left with n kt ln, because otherwise we will have ln 1 upon this exponential factor. So okay, so this will be equal to minus ln of this exponential factor. So that's why I have clubbed two steps here. So logarithmic of exponential beta h cut omega by 2 minus exponential minus beta h cut omega by 2. Okay, so this is further equal to n kt ln. So I'm taking exponential beta h cut omega by 2 outside, exponential beta h cut omega by 2 multiply by 1 minus exponential. So because I'm taking this outside, so I need to multiply here for the second term in the denominator with e power beta h cut omega by 2 in the denominator, and it will go, when it will go to the numerator, there will be a negative sign with this exponent. So it will be this will become exponential minus beta h cut omega. Okay, so let's call this as expression 3, and then we can rewrite equation 3 as a, that is equal to n kt. Now we will expand the logarithmic term, multiply by ln e power beta h cut omega by 2, and then plus ln 1 minus exponential minus h cut omega by kt. Okay, now when t goes to 0, so in that case minus or you can say h cut omega by kt approaches a very large value. So under this condition, exponential minus h cut omega by kt, okay, that is equal to 1 upon exponential h cut omega by kt. Because this quantity is very large, so exponential is going to be very large, so that means this will approach to 0. Okay, so here in the second term we will be left with ultimately under this approximation ln 1. So ln 1 will again it will be equal to 0. Okay, so therefore in when temperature goes to 0, in this approximation the Helmholtz energy, this is approximately equal to n kt ln e. So they will cancel with each other and multiply by beta h cut omega by 2, which is h cut omega upon 2 kt. Okay, so this will cancel with kt. So therefore the Helmholtz free energy per particle, that is equal to h cut omega by 2. Okay, so therefore our correct choice is A here. A is the correct answer here. Let's continue with the next problem. The statement is the partition function of a system of n Ising spins is given as z is equal to lambda 1 power n plus lambda 2 power n, where lambda 1 and lambda 2 are the functions of temperature but are independent of n. If it's given that lambda 1 is greater than lambda 2, okay, the free energy per spin in the limit when n approaches infinity is given as, okay, so here what we are going to do is, as we did in the previous question, we are going to connect the partition function with the Helmholtz energy. Okay, so the Helmholtz energy A, that is equal to minus kt logarithmic of the partition function. Okay, so that means this is equal to minus kbt. Here k, it's a Boltzmann constant, minus kt ln lambda 1 power n plus lambda 2 power n. Okay, because it's given that lambda 1 is greater than lambda 2, so from here what we will do is we will take one term common, minus kt ln lambda 1 power n we are taking outside, and then inside the bracket we will have 1 plus lambda 2 upon lambda 1 power n. This is okay. So now we will make use of the approximation that because lambda 1 it's larger than lambda 2, so this implies lambda 2 by lambda 1 it approaches 0. So in that approximation this term can be neglected here. So this is equal to minus kt ln lambda 1 power n, or this is equal to minus n kt ln lambda 1. So that's the Helmholtz free energy. Okay, so therefore the free energy per spin, so therefore the free energy per spin, that is A divided by N, that is equal to minus kT ln lambda 1. So therefore D is the correct option here. Let's continue with the next problem. The statement is the Hamiltonian of a system of n non-interacting spin half particle is given by this expression, where Sij is equal to plus minus 1 are the component of ith spin along an external magnetic field V at a temperature T such that exponential mu 0 V upon kT, that is equal to 2, the specific heat per particle is. Okay, so here please keep in mind, when the physical quantity per particle is asked in the question, then we need not to work for the expression for the partition function for n particle system. By simply calculating the partition function of a single particle, we can calculate the desired physical quantity. So here we are going to calculate the partition function for only for one single spin. Okay, so if you just take a look at what you have learned in your elementary classes, when you put a for instance magnetic dipole in an external field, so it can either align along the field direction or opposite to the field direction. Okay, so therefore when a spin which is placed in a magnetic field, so its internal energy, the interaction energy of spin, it could be E, that is equal to minus mu dot B or minus mu 0 B when spin is parallel to B, or this could be plus mu 0 B when spin is anti-parallel to B. Okay, so therefore we are having two energy available depending upon whether the spin is aligned along the field direction or opposite to the field direction. Therefore for a single spin, the partition function will be Z1, that is equal to exponential beta E1 plus exponential beta E2. So exponential beta mu 0 B plus exponential minus beta mu 0 B, and this is equal to 2 times cos hyperbolic beta mu 0 B. So let's call this as equation 1. Okay, now the average energy per particle, is given by U, that is equal to minus curly beta ln Z1, and that is equal to minus curly beta of ln 2 cos hyperbolic beta mu naught B. Okay, so this after performing the differentiation, so this will come out to equal to minus, it's simple, you can do it yourself, it's not a difficult task, minus mu naught V tan hyperbolic mu 0 B upon kT. Here K is the Boltzmann constant, please remember it. Okay, so let me call this as equation 2. So now we have obtained the internal energy also. So from here we can immediately determine the heat capacity CV. So CV is equal to du by dt at constant volume. So when you differentiate this with respect to temperatures, we obtain this is minus mu naught V, and then tangent the differential of tangent hyperbolic, that is equal to secant hyperbolic square mu naught B upon kT, and then multiply by mu naught V upon K and differential of 1 by T, which is equal to minus 1 by T square. Okay, so this, after rearranging all the terms, this is equal to KB, minus and minus will become plus, KB or K mu 0 B upon KT its whole square, and then second hyperbolic square mu 0 B upon KT. Okay, and this can be further, because we are provided a value of exponential mu naught V upon KT, so we will rewrite it in terms of exponential functions. Okay, so let me write it on the left hand side. So CB will be equal to K times the Boltzmann constant time K times mu 0 B upon KBT its square, and then second hyperbolic, we will write the second hyperbolic in terms of exponential functions, 4 divided by e power, it's a second hyperbolic, it's the inverse of the cos hyperbolic. Okay, exponential mu naught B upon KT plus exponential minus mu naught B upon KT, and it's it should be 2, and then it's square. So basically then a factor of 4 will come here. Now let me call this as equation 3. Now we are given that exponential mu naught B upon KT, that is equal to 2. Okay, so this implies mu naught V upon KT equals ln2. So with this substitution in equation 3, we obtained the heat capacity per particle, that is equal to Kb times mu B by KT its square. So mu B by KT is nothing but ln2. So Kb ln2 and its square, and then 4 divided by exponential mu naught V upon KT, that is equal to 2. 2 plus exponential minus mu naught V upon KT, so that means 2 plus 1 by 2 its square. So this after expression after solving, we will obtain that this is equal to 16 by 25 Kb ln2 and its square. That's the heat capacity per particle. So therefore D is the correct option here. Let's continue with the next problem. The statement is, which of the following graphs show the qualitative dependence of the free energy Fht of a ferromagnet in an external magnetic field? It's really important to pay attention to this word here, because when there is no magnetic field, then we have some another type of graph, and when the field is applied, the nature of the curve belonging to the free energy, that changes slightly. Okay, and at a fixed temperature which is smaller than critical temperature, where Tc is called the critical temperature. Okay, so here I'm going to discuss 5 different graphs pertaining to different situations of temperature as well as of that of the magnetic field here. Okay, so here let me first draw the graph, and then I will discuss the main point here, and then we will be able to conclude that which one of these 4 options is correct here. Okay, so if it's the H in external field H. Okay, so here this is the so let me write the parameter first. So this is for temperature larger than critical temperature Tc, and along the y-axis in all these curves, it's the free energy. Okay, and here usually we plot the order parameter, and could be magnetization, for instance, for the magnetic sample. Okay, and then we have another curve, but this is valid for a T equal to Tc. It's the same on the y-axis, it's the same pattern, on the x-axis it's the same parameter. Okay, and then we have a third situation where we plot the again the Helmholtz free energy, or the free energy of the system as a function of the order parameter, okay, eta, but this is valid for when temperature is smaller than Tc, okay. And this is the situation when there is no field, okay. So when no field, all these three diagrams, they corresponds to a situation when external field H that is equal to 0, okay. But now when a field is applied and then we monitor the behavior of this system for temperature smaller than critical temperature, the situation is something like this. Okay, so first I'm going to draw the situation when there is a field applied but along the positive direction, okay, something like this. Okay, so here H is greater than 0, the field applied that's along the right hand side, okay, but the temperature is smaller than critical temperature, okay. And along the y direction it's the free energy and it's the order parameter here along the x direction here. And in for the opposite situation we will have a curve like this. So here the energy, the minimum in the free energy, it's along the negative direction, okay. So H, when field is H less than 0, so that means it's along the negative direction. And on the y-axis it's again, it's the free energy, and it is for T smaller than critical temperature, and it's the order parameter here, okay. So now if you just take a look at the statement, it's the behavior of free energy in presence of an external magnetic field. So in principle, depending upon the field direction, in which particular direction, so one of these two options should be the answer should be one of these two options, because here in the options that are given to us, so this is not the correct one here, because this is valid for T greater than Tc. So this curve is valid for when temperature is larger than Tc, and this is not the correct one. This is wrong. This is also wrong. So the only correct option here, it is option C here. But remember that this is valid for when H is equal to 0, not for non-zero magnetic field. But since we don't have any other option here, so that means the most appropriate option is C here, and this is valid when temperature is smaller than Tc. But this corresponds to zero field basically. So therefore C, we will mark C as the right option here. Otherwise, had there been stated directly in the field that in the statement when H is greater than 0, H is smaller than 0, so then one of these two options will be the correct one. So let's take a look at the next problem. So it is from random walk. So the statement is, consider a random walker on a square lattice. So we are having a situation where the walker is moving on a square lattice. Okay, so let me draw the square lattice here so that we can easily understand the problem. Okay. Okay. So let's say this is our starting point, which we are calling as O. Okay. So before continuing further, so as we know that the probability is defined as the probability P, that is equal to favorable outcomes divided by total available outcomes. Okay, now it's given the statement that at each step the walker moves to the nearest neighbor site with equal probability. Okay, for each of the 4 sites. Okay, the walker starts at the origin and takes only 3 steps. The probability that during this walk no site is visited more than 1. Okay, so we have to identify the correct option out of the given 4 option. Okay, so let's assume that in the beginning the walker is at okay, instead of calling this as O, so let's call this point as O. Okay, Walker is at point O, and we call this as origin. Okay, so at this point O, the walker is having 4 different options to take the first step, and these 4 different options, they are marked with the help of arrow. So at O, so we will write here, at O, the number of available path is number of available paths, that is equal to 4. Okay, and the favorable path are all paths here. Favorable paths are equal to 4 here. Okay, so therefore the probability of executing step, the first step, let's call this as P step 1, that is equal to 4 divided by 4. Okay, now suppose the walker has moved along direction O to A. So now the walker has reached the point A here. Now at point A, okay, the available paths are let's see. So either the walker can move in this direction, or in this direction, or in this direction, or in this direction also. Okay, so therefore there are total 4 paths options which are available with the walker here. But then we have to figure out what are the favorable options with the walker at this point A here. Okay, so we have to also ensure the condition that no site is visited more than 1. Okay, so that means the walker cannot follow this path. Okay, so there are only 3 favorable paths. So at this point, favorable paths are equal to 3. Okay, so the required probability of executing step 2 is, that is, the favorable paths divided by total path available. So that is our second result. Okay, now because the walker can move along any 3 preferred direction, and if we assume that walker is moving in the upper direction and it has reached at point B here. Okay, so at point B again, so we have to at point B, available paths are again 4. Available paths is equal to 4, and at this point we have to again figure out the favorable paths. So there will be again 3 favorable paths which will ensure the condition that it will not repeat its journey along the previously traveled path. Okay, so it cannot move along this direction. So the favorable paths here will be three again. Okay, and the required probability of executing step 3, P step 3, will be 3 divided by 4, because all these 3 paths or the steps, they are completely independent of each other. So therefore the required probability of executing these 3 steps will be the multiplication of all these 3 different probabilities, which is equal to 4 divided by 4 for executing step 1. Okay, multiply by 3 divided by 4 for probability for step 2, and then probability for step 3, and this is equal to 9 by 16. So therefore D is the correct option here. So let's continue with next problem. The statement is, an ensemble of non-interacting spin-half particle is in contact with the heat bath at temperature T and is subjected to an external magnetic field. Each particle can be in one of the 2 quantum states of energy plus minus E naught. If the mean energy per particle is given to be minus E naught by 2, then the free energy per particle is given by. Okay, again here we have to evaluate the free energy per particle, and as I said in the previous numerical problem, here again we are going to evaluate the partition function for one single particle. Okay, so the partition function for a single particle, because there are 2 energy states, it's simple to write the partition function Z1, that is equal to e power beta E naught plus e power minus beta E naught, and that is equal to 2 cos hyperbolic beta E naught. Okay, so let me call this as equation 1. Okay, and from here we can immediately evaluate the average energy per particle, that is minus curly beta of ln z1 in principle. Okay, so that is equal to minus curly beta logarithmic of 2 cos hyperbolic beta E naught. Okay, and that is equal to minus E naught tan hyperbolic E naught upon kt. Okay, let's call this equation 2. Now it's given that the average energy U, that is equal to minus E naught by 2. So therefore from here we can conclude that minus E naught by 2 minus E naught by 2, this is equal to minus E naught tan hyperbolic E naught by kt. Okay, so this can be written as sine hyperbolic beta E naught upon cos hyperbolic beta E naught, and this is equal to minus E naught. So we will write sine hyperbolic and cos hyperbolic in terms of exponential function. So multiply by exponential beta E naught minus exponential minus beta E naught divided by 2, and then the cos hyperbolic, which is exponential beta E naught plus exponential minus beta E naught divided by 2. So now this 2 will cancel with 2 and E naught will cancel with E naught, negative will also disappear. So ultimately we are left with the expression that 1 by 2 is equal to exponential beta E naught minus exponential minus beta E naught upon exponential beta E naught plus exponential minus beta E naught. Okay, so after doing the cross multiplication and rearranging the terms, we obtain, so after cross multiplication we will obtain e power beta E naught plus exponential minus beta E naught, that is equal to 2 times exponential beta E naught minus exponential minus beta E naught. Okay, so after solving this expression, I'm writing the final result here because it's simply the arrangement of the terms. Okay, so after rearranging the terms with the negative exponent you keep on the one side, and terms with the positive exponent you keep on the other side. So then we will obtain 3 exponential minus beta E naught, that is equal to exponential beta E naught. Okay, so this implies 3, that is equal to e power beta E naught upon e power minus beta E naught, that is equal to e power 2 beta E naught. Okay, from here we obtain that 2 beta E naught. So this implies, so from here we obtain 2 important results: 2 beta E naught, that is equal to ln 3, and also beta E naught is equal to beta E naught, that is equal to under root 3. I think, let me, okay, anyway we will come to this point at a later stage. Okay, so 2 beta E naught, that is equal to ln 3. Okay, so now okay, I will call this as result 3. Okay, now the Helmholtz free energy is given as A, that is equal to minus kt ln Z1, because we are evaluating the Helmholtz free energy per particle, so that's why the single particle partition function. Okay, so that is equal to minus kt ln 2 cos hyperbolic beta E naught and this upon expansion, this is equal to minus kT ln2, and then minus kT, the second term, ln2 we are taking outside, and minus kT ln cos hyperbolic beta E0 ln. Now I am writing this function in terms of exponential. Okay, so ln of exponential beta E0 plus exponential minus beta E0 divided by 2. Okay, so this can be further rewritten as, so kT is 1 by beta, so minus ln2 upon beta minus 1 by beta ln. So here we will take the LCM, so exponential minus beta E0 is equal to 1 upon exponential beta E0. Okay, so after settling the terms, so it will be equal to exponential 2 beta E0 plus 1 divided by 2 exponential beta E0. Okay, so from here, from the previous step, we can write that A, that is the Helmholtz free energy, that is equal to minus ln2 upon beta minus 1 by beta ln 3 plus 1 upon 2 under root 3. So let me take you back to the previous step. So we have make the substitution here. Basically we are replacing exponential 2 beta E0. So here exponential 2 beta E0, that is equal to 3. So we replace this term with 3 and then plus 1 divided by 2 exponential beta E0. So exponential beta E0 from here, if you just take a look, that is equal to 2 under root 3 basically. Okay, so that's what we did here in this step. So this is further equal to, this is equal to minus ln2. Now we are substituting the value of beta from the equation, this one, equation 3. So beta is equal to ln3 divided by 2 E0. So that's what we are doing in this next step. So beta value is equal to ln3 upon 2 E0. So minus 1 upon ln3 upon 2 E0 ln 2 divided by under root 3. And after this point, it's merely the rearrangement of the terms. Okay, so this is equal to minus 2 E0 ln 2 upon ln 3 plus ln 2 by under root 3 divided by ln 3. Okay, after rearranging the all terms, minus 2 E0 upon ln 3, we are taking it outside ln 3, and inside we are left with ln 2 multiplied by 2 by under root 3. So this is equal to, we are obtaining a very simple expression, minus 2 E0 ln 4 divided by under root 3 divided by ln 3. So this is our answer. That's a Helmholtz free energy per particle. And if you see the correct option here is, it's minus 2 E0 ln 4. Yes, this is A. So A is the correct option here.